are stabilized by adjacent bonded atoms. So adjacent alkyl groups stabilize carbocations. So if we compare our methyl carbocation to the primary, secondary, and tertiary carbocation, the tertiary carbocation would be the most stable. Now, would anyone like to take a guess, or would anyone like to propose a reason for why increasing substitution results in a more stable carbocation? When we can think of a carbocation, when we can view a carbocation as a carbon containing an empty p orbital, what effect have we observed previously when we have adjacent bonded atoms present directly adjacent to an empty p orbital? What effect would help explain this trend where increasing substitution results in a more stable carbocation? What effect did we talk about last class session relating to substitution? So we see in the chat that students are mentioning hyperconjugation and to a lesser extent inductive effects, and that's exactly right. The trend of carbocations becoming more stable with increasing substitution is directly attributed to hyperconjugation effects. So, as a refresher, let's look at hyperconjugation in the context of carbocations. So, hyperconjugation is defined as the overlap of a p orbital with an adjacent sigma bonding molecular orbital. So if we unpack each of these adjacent alkyl groups, we notice that we have a set of adjacent sigma bonds. In this case, this is a sigma carbon-hydrogen bond. To be more specific, it's a sigma carbon sp3 plus hydrogen 1s bond. Now, if we make a model of this structure, so as we notice, we have our p orbital. Does everyone see our p orbital? Okay, now each of these adjacent sigma bonds, the carbon-carbon bond constantly rotates. And as we notice, these sigma bonds can be aligned in a way where they can overlap and they can engage in overlap with our p orbital. This weak overlap that occurs with each of our adjacent sigma bonds on each of our adjacent substituents can in turn allow donation of electron density into our p orbital. So as we notice by this red arrow, what this red arrow is trying to convey is that our adjacent sigma bonding MO overlaps with the empty p orbital and stabilizes the empty p orbital. This in turn stabilizes our carbocation. Now, because hyperconjugation and the strength of this hyperconjugation effect depends on the number of our adjacent sigma bonds, the greater the number of adjacent sigma bonds, which is proportional to the number of substituents, the more stable our carbocation. This is the exact same effect that we observed for radicals, where our electron deficient radical was stabilized via hyperconjugation with adjacent sigma bonds. Note, these bonds don't necessarily need to be a carbon-hydrogen sigma bond. This hyperconjugation effect also works for adjacent carbon-carbon sigma bonds. In each case, we have a weak overlap between our empty p orbital and our adjacent sigma bonding molecular orbital. We see donation of electron density into our empty p orbital, and as a result, that stabilizes our electron deficient carbocation. And this effect becomes more pronounced the more alkyl substituents you have, the more substituted your carbocation becomes, because you have more adjacent sigma bonds to engage in hyperconjugation. Does that make sense? Does that idea look familiar to everyone? Perfect, perfect. So if we think about carbocation stability, the tertiary carbocations are more stable than the secondary, which is more stable than the primary, which is more stable than a methyl carbocation, which is not typically drawn as a plausible intermediate. Okay, let's delve into hyperconjugation a little bit further now. Let's delve into hyperconjugation a little bit further, and let's look at the ethyl cation, for example. Let's look at the ethyl cation, for example. Looks something like this. Now, to truly visualize these hyperconjugation effects, it's important that we draw out and that we clearly are able to visualize each of our sigma bonds in this molecule. So for the ethyl cation, we can expand this structure out into the following drawing for our ethyl cation. Now that we've explicitly drawn out our hydrogens, it becomes quite easy to notice and quite easy to start to depict our hyperconjugation effects. So for our ethyl cation, we have our empty p orbital. And adjacent to our cationic carbon, we have 3 hydrogens. I'm going to draw the molecular orbital picture out just so that way we can help notice overlapping effects. Okay, now what's really important to note is that this carbon-carbon bond can rotate. So in turn, each of our carbon-hydrogen sigma bonds, each of our carbon-hydrogen sigma bonding molecular orbitals can participate in overlap with our empty p orbital and participate in hyperconjugation. Now, as a consequence of this orbital overlap, we have in effect delocalized electron density in our carbon-hydrogen sigma bonds across multiple atoms. Now, this effect is not as pronounced as a formal resonance effect, but as a result of this orbital overlap, we're able to delocalize our electron density and delocalize some of this cationic electron deficient character across multiple atoms. These sigma bonds are overlapping with this empty p orbital in a weak fashion and donating some of our electron density into that empty p orbital. Does that idea make sense to everyone? First, that since this bond is rotatable, each of our carbon-hydrogen bonds can participate, and due to this overlap, we're spreading our electron density over multiple atoms, and we're starting to stabilize this electron-deficient carbocation. Does that idea make sense? Can I get some feedback in the chat? Perfect, perfect. So, in effect, because the hyperconjugated carbon-carbon sigma bond is free to rotate, we can in turn engage in hyperconjugation with each of our carbon-hydrogen sigma bonds. So in effect, we are delocalizing our cationic character and delocalizing our electron density over multiple atoms, similar to what we've seen for resonance effects. So this positive charge is now sort of delocalized over our 4 atoms that are participating in hyperconjugation and orbital overlap. Now, again, I can't stress this enough. This doesn't just work for carbon-hydrogen bonds. It can also work for carbon-carbon and other sigma bonds. So does everyone have a bit more of a clear grasp on how to think about hyperconjugation and how to think about what's actually occurring and the factors necessary for hyperconjugation to occur? Perfect, perfect. So let's talk about resonance effects now. So carbocations are stabilized by adjacent pi systems as the cation can be delocalized via resonance. So, for example, for the following allylic cation, we can in turn draw a valid resonance structure where we've delocalized our cationic charge over multiple atoms. This in turn stabilizes our carbocation. We see plenty of examples of this when we compare a typical alkyl carbocation to an allylic carbocation. Now, further, depending on the number of atoms that you can delocalize your cationic character, your positive charge over, you can observe an increasing amount of stabilization via resonance. So for example, this benzylic cation is abnormally stable. Would anyone like to propose why? If we look at this benzylic cation, would anyone like to propose why this benzylic cation is abnormally stable? What does everyone think? Why am I noting that this benzylic cation has an abnormally high stability? So we see students mentioning the double bonds in the ring. Yep. And what about them? What can we do to this positive charge? How many atoms can we spread this positive charge over in total? Are we delocalizing this positive charge over a relatively few number of atoms or a relatively large number of atoms? So as we note in the chat, we can delocalize this positive charge over at least 7 atoms. Now, of course, these resonance structures are relatively minor contributors, but nonetheless, we are able to heavily stabilize our positive charge via delocalization via resonance. So that's why benzylic cations are abnormally stable. So it's not just important that resonance delocalization is occurring, but the number of atoms that you're delocalizing your charge over and the nature of those atoms. So for example, this quote unquote, what I like to call it almost a doubly vinylic, a doubly allylic carbocation, where it's adjacent to 2 pi systems, is more stable than this carbocation that's just adjacent to 1 pi system. The reason for that is we are able to delocalize our positive charge over 5 atoms in this structure on the left, compared to only 3 atoms on the structure on the right. So the more you're able to distribute your charge over multiple atoms, the more you're able to in turn stabilize that charge as a result of these resonance effects. Now, what's important to consider is not just the fact that we're delocalizing our charge over multiple atoms, but the nature and character of those atoms in terms of electronegativity and other factors that we'll talk about momentarily. For now, does everyone get this idea of resonance effects and how resonance effects can stabilize carbocations? Perfect. So, when we think about substituent effects, we're now going to start to unpack and begin to start to address how different atoms impact carbocation stability. So resonance donors can stabilize carbocations by the donation of electron density into the empty carbocation p orbital. So for example, if you have this adjacent amine group, which has a lone pair present in a filled p orbital that can overlap and donate electron density into this empty p orbital, we can draw the following valid resonance structure where we've stabilized our carbocation, generated a structure with a complete octet, and we've delocalized the charge over multiple atoms. We've now delocalized this positive charge onto nitrogen. As a result of this stabilization via resonance and being adjacent to a resonance donor, the following cation adjacent to this amine group is substantially more stable than your typical alkyl cation. Does that make sense to everyone? We can see a similar effect in this second example, where this adjacent resonance donor oxygen can donate electron density and in turn stabilize our carbocation. Now, the example that I always found really interesting and may serve as something to just put as a small mental note for later, as this theme will come up again when we talk about aromatic reactions, is that halogens can function as resonance donors. So despite their inductive withdrawing character, halogens are perfectly capable of functioning as resonance donors. And that's why often when you start to look at reactions of alkyl halides, and when you start to look at how these halide functionalities affect the regioselectivity of different reactions, you may notice some odd trends where your adjacent halide group can partially stabilize your carbocation. So these resonance donor effects cannot be understated, and they play a big role in later examples when we start to look in future courses even at aromatic substitution reactions. Okay, so just as a summary, carbocations adjacent to resonance donors are stabilized via donation of electron density from the resonance donor into our electron deficient carbocation. Does that idea make sense? Does that idea make sense? Perfect, perfect. So let's talk about inductive effects now. So carbocations are destabilized by electron withdrawing substituents. So what is an example of an electron withdrawing group? The common hallmark electron withdrawing groups are your CF3 groups, your NO2, your nitro groups, your adjacent carboxylic acids, and your adjacent sulfates and other sulfate derivatives. Okay, there are two main factors that allow you to identify an electron withdrawing group. They generally have an atom that is more electronegative than carbon, and in turn, when you have an electron withdrawing group adjacent to a carbocation, a good signpost to look out for and to me start to think about whether or not that adjacent atom it constitutes an electron withdrawing group is to look and see if the atom directly attached to the carbocation contains a lone pair. If it doesn't have a lone pair, then that adjacent atom can likely not function as a resonance donor. And as a result, we have to start to consider inductive effects. So you may say, well, why are electron withdrawing groups so detrimental to carbocation stability? Well, you can think about it from the charge perspective as building up like charges on adjacent atoms, building up positive charges on adjacent atoms is highly destabilizing. Another way that you can rationalize this effect from electron withdrawing groups is that our electron deficient carbocation is destabilized as it loses additional electron density. So in general, if you try to generate a carbocation adjacent to a electron withdrawing group, you're going to end up with a relatively unstable carbocation that in general is not very likely to form. So as we notice, if we have an electronegative atom or an electron deficient atom adjacent to our carbocation, we observe a strong inductive withdrawing effect that in turn destabilizes our carbocation. Does everyone notice in each of these examples for our electron withdrawing group, do we have a lone pair present on our electron withdrawing group? Is there any possibility of resonance donation? Is there any possibility of resonance donation in any of these electron withdrawing groups? What does everyone think? We see students typing in the chat. No, we don't have any adjacent lone pairs, nor do we have any adjacent relatively electron-rich atoms to donate electron density. Okay, so electron withdrawing groups destabilize our carbocations. Perfect. Does this idea make sense to everyone? Perfect. So let's talk now about orbital effects. Now, just like radicals, carbocations are electron deficient species. And if we think about what the nucleus really represents, our nucleus is just a bundle of positive charge, right? In essence. Now, because of that, because carbocations are electron deficient species, they are destabilized the closer they are to the nucleus. Now, if we think about orbital effects, we know that our sp orbital is shorter, stubbier, closer to the nucleus. Our sp2 is a little bit, our sp2 orbital is a little bit longer, while our sp3 is the longest orbital that is farthest from the nucleus. So what we can see from these pictures is that the more s character that we have a shorter orbital that is closer to the nucleus, and this positive charge from our nucleus destabilizes our electron deficient carbocation. So if we look at an sp versus an sp2 versus an sp3, well, let me rephrase this. So I'm going to put this in quotes because of course this hybridization is not, this hybridization, it's not directly sp, because there's no lone pair to fill out the second electron group. But I'm just going to put this in parentheses as sp, quote unquote sp2, quote unquote sp3, because it really emphasizes that as we move from this alkynyl carbocation to an alkenyl carbocation to an alkyl carbocation, we in turn end up with more S character, and in turn, this increasing S character, so this increasing S character observed in our sp-like carbocation results in a less stable carbocation compared to our sp3-like carbocation. If we were to look at the actual hybridizations, this would be sp2, this would be sp, and looking at this carbon, depending on the adjacent substituents, it's a little difficult to assign a formal hybridization for this carbocation. What we do know is that looking at our adjacent atoms and looking at this overall triple bond, we see that both of these carbon atoms in this triple bond contain a large amount of S character, which in turn means our carbocation is in turn located in orbitals that are held closer to the nucleus and are overall less stable. So in terms of orbital effects, the less S character you have, the more stable your carbocation is. Does that idea make sense to everyone? Does this idea of orbital effects make sense to everyone? Okay, so the best analogy I can think of is this trend is the exact opposite for our stability trend for carbon-centered anions, right? Where our sp3 anion is the least stable because this anion is held in an orbital farther from the nucleus. So we actually have already seen this orbital effect trend before when we talked about anions. However, in this case, our orbital effects serve to destabilize our carbocation. Does that analogy make sense to everyone? Does everyone see the parallels between these two trends that we've discussed? Perfect, perfect. So let's now try to apply what we've learned to the following examples. And in each case, we're going to indicate the more stable carbocation. I'll start us off with the first example, and then we'll break off into groups and work on the next few examples. Okay, so first and foremost, comparing these two structures, the major factor that I need to consider are resonance effects. Right? Both of our carbons are secondary, so we don't really have substantial substituent effects. And so we need to look and see, how can we delocalize our carbocation? Well, looking at this structure on the left, it's clear that we can in turn delocalize our carbocation over multiple atoms in our aromatic ring. So we're able to very efficiently and effectively stabilize our carbocation in this leftmost structure via resonance. Comparatively, looking at the structure on the right, we can only really draw one substantially contributing resonance structure. So in turn, if we compare these two structures and we compare the resonance effects in these two structures, we can in turn conclude that structure A would be more stable as we are able to delocalize and stabilize our positive charge over multiple atoms. Does that make sense to everyone? Does that idea make sense? Perfect. So what I want us to do now is to take a look at the following three pairs of structures, A, B, C, D, E, and F. And I'd like you to tell me in each case, which structure is the most stable, lowest energy carbocation, and the why. What effect is mainly responsible for your carbocation stability? So let's take about 3 to 4 minutes to work on this example. You're more than welcome to circle and annotate on our class whiteboard using the annotate feature. But I definitely want to see students sharing their responses in the chat for each pair. And I'd like you to identify which carbocation is lower in energy, more stable, and why. What effect is responsible for this trend? And if you have any questions, don't be shy to ask your questions in the chat or verbally, and we will discuss this example in about another 3 to 4 minutes. And as student responses come into the chat, I'll make sure to voice those student responses and convey them for a broader class discussion. So let's keep working on this example, and we'll discuss in about 3 minutes. So just to help communicate some student proposed responses, we see that in the chat, students are talking a lot about structure A, and they noted that this oxygen can engage in resonance donor effects. We also see in the chat, students are proposing that D is more stable, and their reasoning for that I see students mentioning they're mentioning the positive charge on nitrogen. And we notice that students have further elaborated their explanation and mentioned that in structure C, this carbon is closer to our electron withdrawing group. Okay, so now that we've started to voice some student perspectives, I'd like you to try and comment and continue working through these examples, proposing which of these cations is more stable, lower in energy, and providing your reasoning. And it's really important to talk about your reasoning because the why is more generally applicable than just this specific example. If you know the general trends for carbocation stability, that will serve you well rather than just, oh, this specific carbocation is more stable. So really focus on clearly communicating your reasoning and Don't be shy to disagree with your classmates. If there's a way that you prefer to phrase your explanation and your reasoning for why a carbocation is lower in energy, don't be shy to contribute that to our discussion. So we notice in the chat that students are latching on to this idea that structure F is lower in energy because we have a tertiary carbocation compared to a secondary carbocation. So we see students are beginning to agree. And does anyone have another perspective, another opinion to share when we're looking at carbocation stability? Does everyone agree with the proposed explanations? Is there anything that anyone would like to add? Does anyone have a potentially disagreeing viewpoint? Let's give everyone about another minute, and then we'll talk about these examples. And if you have any questions, of course, do not hesitate to ask. Okay, so let's talk about these examples. In the first case, our primary effect that we need to consider is resonance. So in structure A, as students have correctly pointed out, the alcohol is a resonance donor. And as a result, it can donate electron density and in turn stabilize our carbocation via resonance donation. So cation A is the lower energy carbocation. For the second pair, our primary effect that we need to consider are inductive effects. So looking at inductive effects, this group here, this nitro group, NO2, is a strong electron withdrawing group. So in turn, it exerts a relatively strong inductive withdrawing effect. Now, as we talked about inductive effects, what do inductive effects depend on? Do they care about distance? Do they care about how far away your atom is from the withdrawing group? Do inductive effects care about distance? When we talked about inductive effects all the way back in the chapter on acids and bases, do inductive effects depend on distance? Yes. So then, as we see, in structure C, our carbon is closer to the electron withdrawing group, and in turn experiences a stronger inductive effect, making cation C less stable. Finally, for the third pair, we have a secondary versus a tertiary carbocation, and in turn, we know tertiary carbocations are more stable because we have a greater amount of stabilization via hyperconjugation. So we'll just note that this tertiary carbocation is more effectively stabilized by hyperconjugation. Do these examples make sense to everyone? Do these examples make sense? Perfect. So by understanding the factors that influence carbocation stability, radical stability, anion stability, we can begin to compare and contrast intermediates as well as transition states that we encounter in chemical reactions. So let's do one last set. In this case, we have a trio of 3 carbocations and as well as a pair of 2 carbocations. And one thing that I would really recommend for this second example is to make a model, and I'd like you to really focus on what is the hybridization of each of these carbocations? And try to think about the geometry in this second example. Geometric effects aren't talked about a lot in your book, but I wanted us to address this example because we can see these kinds of geometric effects when we start to look at cyclic systems. So let's work on these two examples for about 3 minutes. I'd like you to tell me which of these carbocations in each set is the lowest energy carbocation and why. And why. And of course, if you have any questions, don't be shy to ask it in the chat. For the second example, you may notice that if you try to make a model of D, you're going to have a little bit of a rough time. And you may notice something really interesting if you try to put together a model of D. So let's keep working on this example, and then we'll discuss momentarily. And as students submit their responses and questions, I'll be happy to communicate it with the rest of the class. So it's great to see we're already starting to see a pool of responses. So to help convey the student responses and help to communicate the student responses, so we know that if we compare our orbital effects, structure A is sp2, structure B is sp, and structure C, looking at our carbocation, we see a substantial amount of S character. So, as a result of these orbital effects, we know that the less S character your carbocation has, the less S character your carbocation has, the lower in energy your carbocation would be. So in turn, that's why we see pretty remarkable student consensus that cation A would be the most stable carbocation from this list. Okay, that was the argument that I voiced from the student responses. Let's keep working on these examples, and then we'll discuss in about another 1.5 to 2 minutes. And don't be shy to disagree with your classmates if you have an alternative proposal. And let's really take a look at this second example, as it's quite interesting, and you may see it on a homework assignment in the future. And really try to think about geometry. Hybridization has a direct impact on your observed geometry. And we have to make sure that our carbocation is geometrically allowed. Does anyone have a proposal for the second set? Does anyone have a proposal for the second set of cations? It's wonderful to see that we have a very interesting comment from one of our students that are noting that they think E is more stable because G is geometrically strained. Okay, that's a very interesting observation. And as we have a nice pool of student responses, let's now discuss. And the moment you see an attempt to make a model of structure D, you're going to notice something a little bit funny. Does this structure D look any bit reasonable to everyone? So looking at this carbocation has an sp hybridization based on the number of charged spheres. Is it very easy to have 180-degree bond angles in a cyclic six-membered ring? Is it pretty easy to have 180-degree bond angles in a six-membered ring? Not easy at all. Does everyone notice how if you try your best to make a structure to represent structure D, that your model kit almost begins to visibly showcase the strain in this ring system? So the reason for that, and the reason for this geometric constraint, is that if we have an sp hybridized carbon sitting smack dab in the middle of our ring, we want to get a bond angle of 180 degrees, right, for our carbocation because it's sp hybridized. It would have a typical bond angle of 180 degrees. But 180-degree bond angles are not permitted, or more correctly, are heavily strained in small ring systems. So due to this substantial amount of geometric strain, carbocation D is less stable. Does this example make sense? I'm really pleased that students have picked up and have observed this idea of geometric strain when you look at different species, be it a cation or an anion. And this is why I like making models, because they often can physically show you the strain in a cyclic system or show you the strain in a system, because you try to put the model kit together, you almost feel the model kit. You feel the strain as the model kit bonds sort of bend and buckle as you try to bend the structure into the correct desired geometry. Perfect. This has been a wonderful set of examples. And any last minute questions on carbocation stability before we continue on with this discussion of radical cation and anion stability in the context of chemical reactions? Any questions on these examples? Okay, if not, let's keep going then. And let's look at the following example. This one's quite interesting because this type of analysis would actually be applied in later portions of this course and in future organic courses. So if you happen to have read ahead or looked at popular sort of articles on organic chemistry, these two structures represent classic intermediates in what is known as a Friedel-Crafts alkylation reaction. Now, utilizing what we've learned about resonance effects, inductive effects, atom effects, I'd like you to tell me which structure has the most stable carbocation. And to help you think through this example, I'd like you to think about which atoms have a positive charge in each structure. And I'm going to give you a little bit of space. I'm going to give you a little bit of space for this, so that way you can draw out on your class whiteboard, because I'd really like you to consider the resonance structures. So where is our cation located in each of our resonance structures, and how is our cation stabilized or destabilized by this electron withdrawing group. So I'd like us to work on this example for about 3 to 4 minutes. This is really showcasing the utility of how we've learned this idea in terms of carbocation stability, and we now can apply it to an example and a problem-solving process that we'd use later on in the class. So I'd like you to tell me which of these carbocations is more stable and why. And to do that, you may want to draw some resonance structures and try to figure out what atoms contain a substantial amount of positive charge. And remember, you can share your proposed resonance structures using the annotate tool. So let's get started on this example. And as there's plenty of space in the class whiteboard, multiple students can draw out their resonance structures. And from that information, I'd like you to tell me which of these two cations is lower in energy, which of these two cations is more stable. And if you have a question or if there's any part that you're unsure about in this example, don't be shy to ask it verbally or in the chat. And as a reminder, the annotate tool is available under the meeting options function in Zoom. So this is a nice capstone example, similar to what you may see on an exam, as it really helps apply a lot of the effects and concepts that we've learned in terms of carbocation stability. And I'll put some labels, A and B, and you're more than welcome to propose in the chat or verbally which of these two carbocations you think is more stable, lower in energy, and why. The why is the important part, as that's what you take and can use in future problems. And don't be shy just to try to convey just some things that you've observed, just some observations, any comments that you have. We can build on those as a class if we're stuck. And we'll discuss this example together as a class in about 3 to 4 minutes. But I'd like to see some students try to start this discussion or try to at least draw out some resonance structures, and I'll help push us along in the discussion if we're ever getting stuck. And of course, if there are any questions, don't be shy to let me know. And a good place to start for this problem is to start drawing out some resonance structures for each of these two molecules. So I can start us off, give us a small push to get us started. We can, of course, kick our double bond across and draw the following resonance structure. Can we draw a few more resonance structures for both these two molecules? Can we draw a few more resonance structures for these two molecules? So we have a student noting in the chat that they think that B is the more stable carbocation. We have a proposal that B is the more stable carbocation. And their reasoning is that in A, the carbocation is closer to the electron withdrawing group. Now, that is a very interesting point to bring up. And to justify and fully investigate that point, let's draw out a few more of our resonance structures to really see, in structure A, is our carbocation really always held closer or adjacent to the electron withdrawing group? Let's try to run with that idea. And to help us visualize that, let's draw out some resonance structures. And is everyone comfortable? Is everyone able to utilize the annotate tool? It's again under the meeting functions. And if you need more space, I'd be happy to pan down. You can also share a picture of your proposed resonance structures, and I'd be happy to convey it in front of the class. What about some resonance structures for structure B? Does anyone have any proposed resonance structures for structure B? Okay, so a student just sent me a picture of their proposed structures. Let me take a look. Perfect. So allow me to convey, a student sent me a photo of their proposed resonance structures. So allow me to convey what that student has proposed. So they propose the following set of resonance structures for structure B. So first they kick their double bond across to generate the following resonance structure. They then kick the double bond across a second time, and that in turn yielded the following. Let me make sure my bond geometries are appropriate. The following resonance structure. Okay, so these resonance structures are quite important to consider because it allows us to look at the location of our carbocation. It allows us to look at the location of our carbocation relative to the electron withdrawing group. Now, what do we notice if we compare structure A and structure B? Which structure has our carbocation closest or adjacent to our electron withdrawing group? Which structure has our carbocation closest or adjacent to our electron withdrawing group? Building off of the resonance structures that your fellow classmates have provided, which structure, which set of structures has the carbocation closest to your electron withdrawing group, A or B? A, right? So as we can see, carbocation A has the cation adjacent or close to the electron withdrawing group, which in turn leads to a less stable cation. So as your classmate originally noted, as a result then, because the carbocation in structure A is closer to the electron withdrawing group, which cation is lower in energy then, A or B? Which cation is more stable? Which cation is more stable then? B, exactly right, exactly right. So we conclude then that B, cation B, is more stable. And this logical idea of drawing out resonance structures, looking at how in each resonance structure, how do the substituents influence our cation stability? This kind of analysis will serve you well when we start to talk about regioselectivity for reactions. Why do we observe selectivity for certain positions in our molecule? Does this example make sense to everyone now that we've drawn out the resonance structures and we've visualized how our charge is distributed? Does that make sense to everyone? Oh, whoops. So looking, yep, okay, perfect. Wonderful. So I greatly appreciate how everyone has chipped in our discussion. We really couldn't have completed this without contributions from different members of the class, both in terms of the resonance structures, some of the logic that got us started in looking at this problem. And this kind of example is the kind of analysis that we typically have to do on an exam. Any last minute questions on this example? Okay. So, as our last example before we close out today's session, now that we've seen an example where we've drawn out resonance structures and we've analyzed those resonance structures to predict the more stable carbocation, let's apply what we've learned to the following pair. So we have structure A and B. This is another sort of textbook Friedel-Crafts intermediate. And I'd like you to tell me which of these two cations is more stable. And you may need to draw out some resonance structures in order to completely answer this question. So which of these cations is more stable and why? And again, don't be shy to annotate and draw out using the annotate tool, or to share your proposed reasoning in the chat or verbally. And if you have a question, I'd be happy to answer any questions that you have or convey your responses in front of the class to advance our discussion. And we'll discuss this example in about 2 minutes. And again, we're trying to answer the question, which of these cations is more stable or lower in energy? And just as a hint for everyone to keep in mind, this adjacent ether functionality is a resonance donor. So what does everyone think? Does anyone have a proposal for the lower energy carbocation? Does anyone have a resonance structure that they would like to share? I'll chip in and I'll provide one resonance structure for structure B. Does anyone have any other resonance structures drawn or any other proposals for the lowest energy carbocation in this pair? So to help us start, oh, okay, perfect. So we have a student that proposes that structure B is more stable because the carbocation is closer to the electron donating group. Okay. Do we have any other proposals in the chat for the more stable carbocation? So to help us branch out this discussion, let's draw a few of our resonance structures. So for structure A, we can see the following resonance structure. We can also observe, let's zoom out a little bit so we can observe the resonance structures as a whole. Okay, so looking at these resonance structures for A and B, what do we notice if we compare the resonance structures for A and B? What do we notice in terms of stabilization of our cation? Is there something that differentiates structure A and B? Does anyone notice something different if we compare structure A and B? We're thinking about this idea that this adjacent ether functionality, is a resonance donor, right? So we have this idea that this ether functionality is a resonance donor, correct? So then my question to all of you is, in which structure is the ether able to donate electron density to our cation via resonance? In which case are we able to observe resonance donation? So we have the chat noting that in structure A, we have our carbocation directly adjacent to our resonance donor. And as a result, we can stabilize our carbocation via resonance donation. Because carbocation A can experience stabilization via donation from our resonance donor, while structure B, as we notice, cannot. Structure A, carbocation A, is more stable. Does that logic make sense? Does that logic make sense to everyone? Perfect. So this is a great point for us to take a quick